Hi everyone, welcome to Unacademy. Myself, verified plus educator in the Unacademy platform, Sathyamoorthy. Let's crack it. Today in this session, we are going to discuss about the discussions about the longitudinal vibration. Today we are going to discuss about the longitudinal vibrations, damped longitudinal vibration as well as undamped longitudinal vibration. There are two conditions are there. Today we are going to discuss about the damped longitudinal vibrations category. Before entering into the damped longitudinal vibration, first we are going to have the few concepts in the undamped condition. Based on this condition, we are moving into the damped condition. First, we are going to have the simple pendulum category. The natural frequency of the simple pendulum is given as, consider a simple pendulum of string length L pivoted at one end and having a concentrated mass M at the other end. So here that's a simple pendulum category. The simple pendulum is connected at one end to the pivoting point, another end at the mass center. It's L. When we are giving the initial force to the pendulum, it oscillates few times. So when it oscillates, the forces acting on the mass due to the initial force given it as the total force is m into g. Total force m into g is resolved into two components: vertical force as well as horizontal force. So vertical force, force perpendicular to the line of stroke, it's a mg into sine theta. Horizontal mg into cos theta. Along the string length, mg cos theta. Perpendicular to the string length, mg sine theta. Now we know that according to the D'Alembert principle, we have to add the forces. Now the accelerating torque or inertia torque acting upon the pendulum here, I into d square theta divided by dt square. Here I, moment of inertia, mass moment of inertia, d square theta divided by dt square, angular acceleration of the pendulum, where I is equal to ml square, mass moment of inertia, mass into radius of gyration square. Here the radius of gyration square is equal to length of the string. The length is pivoting point to the mass center is called as total length of the string. So here radius of gyration is equal to the string length. The restoring torque, when we are giving the initial force, so again due to the some external force, it oscillates. Again it comes to the original force due to the restoring force. The restoring force is given it as per the potential energy. We know that when load acting on the mass, the potential energy it retrieves the position into the original position. So here mgl into sine theta. We know that mg here force into perpendicular distance, it gives the moment. Here force into force, mg sine theta into perpendicular distance L. mg sine theta into L. We are considering into the mg sine theta and L. Here oscillation is very small. So here the theta is, sine theta is very small. So we are taking it as theta. mg theta into L. According to the D'Alembert principle, inertia torque plus all the external force acting upon the system of body is equal to 0. We know that inertia torque is I into d square theta divided by dt square. The external force is equal to the restoring torque. How much force we are giving to the pendulum, that much force, okay, again retrieves the position into the original position. The external torque is given it as force into perpendicular distance, that is mg L into theta. Now we know that I is equal to mass into radius of gyration square, m L square. Now substitute the I value, then divided by both side on m L square. So m L square divided by m L square cancel. Coming into this category, mgl divided by here mgl divided by ml square, mg L divided by m L square. So m cancel, L and square cancel, divided g divided by L. The above equation represents the differential equation of motion for the simple pendulum. The above equation represents the differential equation of motion for the simple pendulum. We know that for simple harmonic motion, d square x divided by dt square plus omega n into x, that is equal to 0. Coming to this equation, d square x divided by dt square plus omega n into x. Compare these two equations, then omega n here square, omega n square, as per the simple harmonic motion it is square, omega n square. So omega n square, equate these two equations, what we are getting here, omega n square is equal to g divided by L. So omega n is equal to g divided by L. We know that the natural frequency of the system Fn is equal to omega n divided by 2 pi. Now substitute the omega n value is equal to g divided by L. So this equation belongs to the simple pendulum equation. But coming into the category of compound pendulum, it is different. Pivoting point from mass center to the pivoting point different length, radius of variation different. So we have to take different formula for the compound pendulum. We will discuss in the forthcoming slides the compound pendulum. Next we are moving into the equivalent spring stiffness. Coming into the equivalent spring stiffness, when the two springs are in series connection, so we are identifying the equivalent stiffness for the two springs is given at image of, they are connecting the mass bottom of these two springs. The weight of the mass pulls the two springs simultaneously, so there will be a deflection, total deflection in the both the spring is equal to delta is equal to delta 1 plus delta 2. We know that, but deflection is equal to load by stiffness, that is total deflection is equal to load by total spring stiffness. Then delta 1 is equal to load, total load acting on the spring divided by stiffness of the spring 1 plus W divided by S2. Now take this W commonly from the equation, then W, LHS, RHS, W cancel. The remaining thing 1 divided by S equivalent is equal to 1 divided by S1 plus 1 divided by S2 from this equation here. But the most of the competitive question paper we are getting it as stiffness is equal to notation K. Here I have choose the notation for the stiffness is equal to S. The equivalent spring stiffness for the system is given as from this equation. Terminate. Yes. Here from this equation the S equivalent, S spring stiffness equivalent is given as S1 divided by S2, S1, S2 divided by S1 plus S2, S1 plus S2. So this is the equivalent spring stiffness. And the springs are in parallel connection. This belongs to the springs are in series connection. This springs, the mass is connected at bottom of these two springs connected in the parallel mode. The equivalent spring stiffness, we know that here total load is shared by the two springs, so the total load W is equal to W1 plus W2. But the stiffness load, we know that formula, load is equal to deflection into stiffness, again the same formula. Now as per this formula we are getting S equivalent is equal to S1 plus S2. So these are the series and parallel. Now I am giving one more question in this diagram. Okay, tell about what category it is, either it belongs to the series or parallel. Here mass M connected here, the two springs are connected in this manner. What about this? Okay, either it is series connection or parallel connection, S1 and then S2. What about this diagram? It is series or parallel? Okay, learners who are watching the live session, you can give your answers through the live chat box. Here live chat available in the YouTube page. Okay, in the bottom of your screen you are getting the live chat option. If you are having any doubt, then you can ask your doubts immediately through the live chat box. The purpose of the class to make you understand the concept of longitudinal vibrations. So if you are having any doubt, immediately ping your doubts through the live chat box. Myself Sathyamoorthy, verified plus educator in the Unacademy platform. Then myself Vivekanandan, Suresh Kumar, Bhubala Krishnan. V4 are together handling the rank booster course for mechanical engineering 2020 gate examination. That course starting at December 13, 2020, December 13, sorry, 2019. So it goes from December 13, 2019 to January, okay, up to the January 2020. So watch it, so you can get the good marks. In this course, we are going to cover the engineering mechanics, SOM, strength of material, theory of machines, and industrial engineering, castings, materials, and manufacturing streams. These all contents will be covered in this course. So please stay tuned the Unacademy platform. Myself Sathyamoorthy. Install the Unacademy Learning app in your Android mobile. Search the name Unacademy Learning app in your Play Store, Google Play Store, and install it. And search my name Sathyamoorthy space V in the search bar. Then follow me. Then you get notified for each special classes as well as regular classes in the Unacademy. Okay. Now coming to this category, this problem belongs to either it is belongs to the series or parallel connection. The thing is the shortcut methodology in order to identify the series or parallel connection. In the series connection, if you are cutting any one of these spring, the mass is disattached from the support. But parallel connection, if you are cutting any one of the spring, again the mass is handled with the support with application of the other spring. Coming to the series connection, if you are cutting the S1, the mass is removed from the support. If I am cutting S2, again the mass is removed from the support. So in order to keep the mass with the support, we have to keep the both the spring. Okay. But coming into the parallel case, if you are cutting in only one spring, again the remaining spring will hang the system. So in order to remove the mass from the support, we need to cut the both the spring at the same time. Simultaneously we have to cut the both the spring. Then only the mass will be removed from the support. So here coming into this category, if you are cutting the S1 alone, again the mass is hanged with the support with the application of S2. Here with application of S2. Okay. So if I am cutting S2 alone, again the mass is suspended with the support with application of S1. In order to remove the mass from the support, we have to cut the both the spring simultaneously, S1 and S2. So in this category, it belongs to the parallel connection. So we can use this shortcut in order to identify the series connection or parallel connection. The given problem belongs to the either series or parallel connection. Now here when the mass is suspended to a spring, so in this category the problem based on this here. Here we need to identify the natural frequency when the mass m and S1 spring, the stiffness is equal to 1500 Newton meter. The frequency is given as, so we have to identify when the mass is suspended at bottom of two springs. Here S1 and S2. Here the equivalent spring stiffness is given as S1 into S2 divided by S1 plus S2. So substitute the S1 is given as in this problem. The thing is S1 is equal to 1500 Newton per meter. 1500 Newton per meter. S2 is equal to 900 Newton per meter. Mass is equal to, coming to the mass is equal to 12 kg. M is equal to 12 kg. When you are substituting all this value here, what we are getting here, the thing is equivalent spring stiffness is equal to S1 S2 divided by S1 plus S2. And substitute the spring stiffness value S1 and S2 and M value in the equation. Fn is equal to 1 divided by 2 pi into root of S equivalent divided by M. That is equal to 1 divided by 2m into root of 5625 divided by 1 2. When the mass is fixed in between the two springs, okay, already we have discussed the same kind of question in the previous slide, the same thing. So it is again, it's a parallel connection. For the parallel connection, we have to add both the spring stiffness values S1 plus S2. Again substitute the S1 and S2, sorry, S equivalent to the frequency equation. The Fn is given it as 1 divided by 2 pi into root of S equivalent divided by M. That is equal to 1 divided by 2 pi into root of 2400 divided by 12 is equal to 2.25 Hz. 2.25 Hz. Now next one. When the mass is suspended at the bottom of two springs in parallel, the mass is suspended at the bottom of two springs in parallel. So again it is also parallel connection. Then again S1 plus S2, where the spring stiffness values were added. Then substitute this value here. Then again the spring stiffness frequency the same value. The same kind of question. This question was asked in the GATE 2017 Mechanical Engineering question paper. Coming to this category, a mass M is attached to two identical springs having spring constant K. A mass M is attached to two identical springs having spring constant K as shown in figure. The natural frequency omega of this single degree of freedom system is. Here we know that when the springs are connected in parallel mode, the total stiffness value given it as the K equivalent. K equivalent is equal to K1 plus K2 value. Here K1, K2 both are K, so K plus K is equal to 2K. K plus K, both values equal to 2K. Now substitute the value. We know that omega n is equal to root of K equivalent divided by M. K equivalent divided by M. Now K equivalent equal to 2K. So root of 2K divided by M is the answer for the given question. So option A is the given. So option A is the answer for the given question. Next we are moving into the next question. Yes, here it is GATE 1994 question. Okay, this question was asked in the GATE 1994. I think the question is hiding behind my picture. So it is GATE 1994. I am giving it as it is GATE 1994 mechanical engineering question. GATE 1994 mechanical engineering question. Here, if mass is attached to a light spring oscillates with a period of 2 seconds, okay, behind it was hiding, the mass is increased by, here mass is increased by, here the question, the hidden content behind my picture, if mass is increased, if mass is increased by 2 kg, the period increased by 1 second. The value of m is, here we need to identify the mass value. First, the mass m, the natural frequency, what we are giving a time period. We know that time period is equal, frequency is equal to frequency Fn is equal to 1 divided by time period. Here time period is equal to 1 divided by 2. Now it is 1 divided by 2. The frequency is equal to 1 divided by 2. The frequency is equal to 1 divided by 2 pi into root of S. Here I am taking it as spring stiffness is equal to K. We can select K or S. Stiffness is equal to K divided by M. So here the stiffness value is equal to 1 divided by, frequency is equal to 1 divided by K divided by M. When the mass is increased by 2 kg, when we are putting plus 2 in the mass value, the time period increases by 1 second. So when we are increasing 1 second, 2 plus 1, we are increasing the mass value by 2, the time period increases 2, that is K divided by M plus 2, K divided by M plus 2. When you are increasing the mass value 2, this value increases by 3. Now, the thing is, we have to correlate these two two things here in order to identify the value of m. Yes. Now we have to equate these two equations here. 1 divided by 2 and 1 divided by 3. Now from this equation, what I am giving, I am keeping this 1 here. So 1 is equal to 2 divided by 2 pi into root of k divided by m. K divided by m. I am taking it as this equation is equal to first equation. Then second one, from this equation I am keeping this 1 here. 2 plus 1 is equal to 3. 3 divided by 2 pi into root of k divided by m plus 2. K divided by m plus 2. I am taking this equation is equal to equation 2. Now equate the equation 1 and 2. When you are equating the equation 1 and 2, what we are getting here? From this equation, I am writing it in the different color. Watch it carefully. Now 2 divided by 2 pi into root of k divided by m is equal to 3 divided by 2 pi into root of k divided by m plus 2. M plus 2. Now 2 pi cancelled. 2 pi cancelled. Now the thing is we have to cross multiply these things here. We are cross multiplying these things. What we are getting here? Now root and root cancel. Here m plus 2, m plus 2. What I am doing here? I am cancelling the values here. Now root value cancel. Okay. So here from this equation, here m into 3m is equal to 3 into m is equal to 2 into m plus 2. 2 into m plus 2. The values we have to subtract the value here. This here. So the thing is we have to take this. We have to multiply this 2 into inside. Wait a minute. Yes. Yes, I'm writing here. Wait a minute. Yes, from this equation, yes, here from this equation, wait a minute, I will select the color, then we will discuss. 1 divided by 2 is equal to 1 divided by 2 pi. Here we know that omega value 1 divided by 2 pi into root of k divided by m. We are increasing the value. We are increasing the value k divided by m plus 1. This equation equal to here. Now we have to cross multiply it. We are equating this. Take this 2 into the numerator, again this 3 into the numerator. Now we have to cross multiply the things. We are cross multiplying things. What we are getting here? Yes. 2 divided by 2 pi. 2 divided by 2 pi into root of k divided by m is equal to 3 divided by 2 pi into root of k wait a minute, it is divided by m plus 2. It is m into 2. Now cancel this 2 pi and 2 pi, 2 pi and 2 pi. Now we have to cross multiply it here. Taking this value, when you are cross multiplying it, what we are getting here? It is, again take this value here, it is 2 here, 3 divided by 2, 3 divided by 2, 3 divided by 2 is equal to, yes, wait a minute, there is some mismatch in the pen. Yes, now is it clear? Yes. Now cancel it from this equation. The remaining thing, these are the values. Square on the both sides. When you are squaring it, 4. The root value here again k divided by m. K divided by m. Wait a minute, I will switch on the chart. Yes. Is equal to, when you are squaring the 3, 9. Then squaring the root k divided by m plus 2, it is k divided by m plus 2, k divided by m plus 2. This is the equation now. Now cross multiply the values. When you are cross multiplying the values, what we are getting here? Now 4k divided by m. The cross multiply m and k. Now k and k cancel. Now cross multiplying the values here. Here 4 into m plus 2 is equal to 9m, is equal to 9m. We are multiplying it. Here what we are getting? Here 8. 8 4m plus 8 is equal to 9m. From this equation, it is m. Multiplying it, m is equal to 8 divided by 5. M is equal to 8 divided by 5. Now simplifying this equation, 8 divided by 5 is equal to 1.6. The answer is 1.6 kg. Okay, then if you are having any doubt, then immediately ping your doubt through the live chat box, so I can help from my end. Yes, next question to you. Now, in this question, a rod of uniform diameter is suspended from one of its end in vertical plane. The rod is suspended from vertical plane. The mass of the rod is m and length L. The natural frequency of the rod in hertz for the small amplitude is. Okay, what about the answer? Already we have discussed for the simple pendulum. The amplitude is given it as the frequency of amplitude. The natural frequency is equal to 1 divided by 2 pi, 1 divided by 2 pi into root of g divided by L. So this is the correct answer for the given question. Next we are moving into the next topic. Here damped free longitudinal vibrations. Damped free longitudinal vibrations. In this category we are going to have the definition damping, types of damping and damping coefficient and all. Now damped free longitudinal vibration. We know that the free longitudinal vibrations, after giving the initial force, after removing the initial force that is initially applied on the system, after removing the initial force, again the body continues to vibrate some period of time. That vibration is called as free vibration. And the damper is connected to the free vibrating body, and the total vibration is called as damped free longitudinal vibrations. Coming to the damping here, damping, the damping can be defined as the resistance offered by a body to the motion of a vibrating system. Damping can be defined as the resistance offered by a body to the motion of a vibrating system. The types of damping given it as viscous damping, Coulomb or dry friction damping, solid or structural damping. Fourth one, slip or interfacial damping. So these are the damping conditions used here. Types of damping: viscous damping, Coulomb or dry friction damping, solid or structural damping, slip or interfacial damping. Then damping coefficient C, the damping force per unit velocity is known as damping coefficient. Now, the damping can be defined as the resistance offered by a body to the motion of a vibrating system. As per the damping definition of the here damping coefficient is given it as damping force per unit velocity is known as damping coefficient. The mathematical relation here C is equal to here C damping coefficient is given it as damping force per unit velocity. The damping force is equal to from C into unit velocity. The velocity is if displacement is equal to x, the velocity is given it as dx divided by dt. The damping force is equal to C into dx divided by dt. Dampers in series connection. Coming to the dampers in series connection. These are the dampers in series, dampers in parallel. The same thing what we have discussed in the spring mass system. The spring mass system, the total equivalent spring stiffness, the same category. The only difference, instead of spring, here along with the spring we are using the dampers. So that each damper having some specific damping coefficient. Here the three dampers C1, C2, C3. Here damping coefficient of these three dampers. Okay. Then the equivalent damping coefficient for the series connected dampers are given it as same formula. The 1 divided by the same formula what we have used in the series connection of the springs. 1 divided by C equivalent is equal to 1 divided by C1 plus 1 divided by C2 plus 1 divided by C3. So these are the dampers connected in series connection. Next one, dampers in parallel. The C equivalent is equal to C1 plus C2 plus C3. When the dampers are connected in parallel connection, C equivalent is equal to C1 plus C2 plus C3. Now the dampers are given it as here spring S1. The parallel dampers are with damping coefficient C1, C2 and C3. So we are adding the damping coefficients. Frequency of free damped vibrations are given in terms of, now when you are connecting the dampers in the spring mass system with damping coefficient C, the equation is given it as here M mass suspended from the spring, S stiffness of the spring, delta static deflection of the spring. We know that the load by stiffness, load mass into gravitational force, X displacement of the mass from the mean position after t time. So after giving the external force, the displacement of the mass from the mean position after t, here x. C damping coefficient. C is given it as damping coefficient. The various forces acting on the mass is given it as various forces acting on the mass. Accelerating force is equal to mass into acceleration. Ma accelerating force here A d square x divided by dt square is equal to inertia force. Damping force given it as C into dx divided by dt, damping force. The damping force it is defined as damping coefficient into unit velocity. Spring force or restoring force is given it as S into x. The first acting in the upward direction, we know that they are putting the mass in the downward act. The restoring force again opposite to the applied force that was acting in the upward direction is S into x. According to the D'Alembert principle, we know that according to the D'Alembert principle, the vector sum of all the inertia forces as well as external forces acting upon the system of rigid body is equal to 0. So as per the D'Alembert principle, inertia force plus summation of external forces. You know that inertia force is equal to mass into acceleration, m into d square x divided by dt square, plus external forces. There are two forces acting on the mass. One is damping force due to the damper, then restoring force due to the spring. The damping force is equal to damping coefficient into unit velocity into s into x is equal to 0. Here d square x divided by dt square plus c divided by m into dx divided by dt plus s divided by m into x is equal to 0. So this is the required differential equation for the damped free longitudinal vibration. Required differential equation for the damped free longitudinal vibrations. The next one is the next very important definition: critical damping coefficient. Sorry, wait a minute. Yes, critical damping coefficient. C suffix C is equal to 2m omega n. The damping ratio or damping factor as per the critical damping coefficient and actual damping coefficient is given as. It is the ratio of actual damping coefficient to the critical damping coefficient. Yes. Now, as per the critical damping coefficient data, we are having the few relations in between the zeta and Cc. When zeta is greater than 1, that means the actual damping coefficient is greater than critical damping coefficient and system is said to be over damped. Second one, when zeta is equal to 1, that is C is equal to Cc, the system is said to be critically damped. When the critically damped, the damping is very minimum, but oscillation, it arrests the oscillations or vibration. When zeta is less than 1 or C actual damping coefficient less than the critical damping coefficient, the system is said to be underdamped. The system is said to be underdamped. The equation of motion when zeta greater than 1, overdamped system. The equation of motion when zeta greater than 1, overdamped system. For the overdamped system equation of motion, x, here the x is the motion of the particle from the mean position. X is equal to C1 into e power minus zeta plus root of zeta square minus 1 into omega n into t plus C2 into e power minus zeta minus root of zeta square minus 1 into omega n into t. When zeta is equal to 1, critically damped system. For the critically damped system, as per the differential equation, ordinary differential equation, the equation derived here, the derived equation is equal to C1 plus T into C2 into e power minus omega n into T. C1 plus T into C2 into e power minus omega n into T. Then last one, when zeta less than 1, underdamped system. When zeta less than 1, underdamped system, that x is equal to capital X into e power minus zeta omega n into t into sine omega d into t plus pi. Omega d into d, omega d into t plus pi. Next one, we are moving into the logarithmic decrement. So very important concept. Based on the logarithmic decrement, we are going to have the problems based on the logarithmic decrement. Yes, the logarithmic decrement. First, I am reading the first three paragraph important definitions one by one. Listen it carefully. Logarithmic decrement is defined as the natural logarithmic of amplitude reduction factor. So first, this uh, definition itself you should not understand anything. Okay, I will explain it. Wait a minute. Logarithmic decrement is called as natural logarithmic. Now we are moving from the bottom paragraph. Here it's a diagram for the underdamped system. Here it's one cycle. This point to this cycle, one cycle, and from here to here another cycle. Cycle 2, cycle 3. So here when time is equal to 0 at initial position, the amplitude, that means maximum displacement of the particle from the mean position, amplitude is equal to x naught at time t equal to 0. After completing the one cycle, that means one revolution, after time t 1 seconds, the amplitude is equal to x1. Again, after completing the second cycle, at the end of the second cycle, the amplitude of the vibration is equal to x2. Okay, now it's an underdamped system. In any underdamped system, it is observed that the ratio of any two successive amplitudes, the ratio of in an underdamped system, the ratio of any two successive amplitudes in a underdamped system always constant. So any two amplitude. Now coming to the any two. Now starting from the x1 successive amplitude, the x1, the successive amplitude x0, then x1. Successive amplitudes are equal. Successive amplitudes are in equal value. So x1, the successive amplitude x2. Like that is equal to x2 divided by x3. So the equation is given in terms of up to the xn divided by xn plus 1. So the successive amplitude in the underdamped system always constant. Now coming into the second paragraph. The amplitude reduction factor is the ratio of any two successive amplitude on the same side of the mean position in an underdamped system. The amplitude reduction factor is the, coming to the amplitude reduction factor, the amplitude reduction factor is the ratio of any two successive amplitude. So here we may select it as x0 divided by x1 or x1 divided by x2 or x2 divided by x3 or xn plus xn divided by xn plus 1. The amplitude reduction factor is ratio of any two successive amplitude. So we are taking the amplitude reduction factor, ratio of the successive amplitude. Again coming to the first paragraph. Logarithmic decrement is defined as natural logarithmic of amplitude reduction. What is meant by amplitude reduction factor? It is successive amplitude of the ratio of the successive amplitude. So, but the successive amplitude ratio from the third graph obviously constant in the underdamped system. When you are taking the natural logarithmic, here we are denoting that logarithmic decrement delta. So delta is equal to natural logarithmic of amplitude reduction factor. Delta is equal to ln of the amplitude reduction factor. You can take it as xn plus xn divided by xn plus 1. Xn plus 1. So this is the equation. Okay. Yes, delta is equal to ln into xn divided by xn plus 1. Now, from this equation, maximum amplitude, that is equal to x is equal to e power minus zeta omega n into t. How we are deriving the maximum amplitude? As per the discussion, it's a displacement for the underdamped system equation. The displacement equation for the underdamped system. When it is maximum, when sine this value is equal to 90, when from this equation omega d into t plus pi is equal to 90, that is sine 90 is equal to 1. When it is equal to 90 degree, it is maximum value. That means maximum amplitude. So here the maximum amplitude is given it as x into e power minus zeta into omega n into t. Let x naught is equal to the maximum amplitude at the start of the motion when t is equal to 0. Coming to this equation, x naught is equal to maximum amplitude at the start of motion. Maximum amplitude at the start of motion when t is equal to 0. When time t is equal to 0. x1, coming to the x1 is equal to maximum amplitude at the end of the first oscillation. Here x0 maximum amplitude at time t equal to 0, x1 at end of the time t1, x2 at end of the time t2. Now substituting t is equal to 0 in this equation, x0 is equal to capital X because e power 0 is equal to 1. When you are substituting t1 is here t is equal to 1 or t is equal to t1, then the value is given as x into e power minus zeta into omega n into t1. Then t2 t is equal to 2, x2 is equal to capital X into e power minus zeta omega n into t2. The ratio of successive amplitudes, coming to this equation, the ratio of the two successive amplitudes is given as x1 divided by x2, that is equal to capital X into e power minus zeta into omega n into t1 divided by capital X into e power minus zeta into omega n into t2 is equal to e power minus zeta into omega n into t1 minus of, here the denominator is taken into the numerator, so we have to put the minus in the power. So when you take this minus into minus plus, now t2 minus t1, we are changing the equation omega zeta into omega n, we are keeping this term commonly outside, and into t2 minus t1. We know that t2 minus t1 is equal to damped time period. Coming to the equation t2 minus t1, we are taking into the equation is equal to t2 minus t1, damped time period. Damped time period. And substituting it, then we are substituting dt as per the dt value. I'm sorry, x1 divided by x2. Now this value constant. We know that the amplitude reduction factor in the underdamped system obviously constant for the successive amplitudes. Now the logarithmic decrement is given as natural logarithmic of xn divided by xn plus 1, that is equal to ln of e power minus zeta omega n into dd, omega n into dd. So zeta is equal to delta is equal to zeta into omega n into dt. Now the relation between the, now substitute the dd, the damped time period is equal to 2 pi divided by omega d. The relation in between the natural frequency of undamped vibration and damped vibration is given in terms of omega d. It's a natural frequency of damped vibration is equal to 1 minus zeta square into omega n. Now substitute the value root of 1 minus zeta square into omega n instead of omega d in this equation. Now cancel omega n. The zeta, the logarithmic decrement is given as delta is equal to 2 pi zeta divided by root of 1 minus zeta square. Delta is equal to 2 pi zeta divided by 1 minus zeta square. Note, if the system executes n cycles, coming to this equation, if system executes n cycles, the logarithmic decrement delta can be written as delta is equal to 1 divided by n into ln of x naught divided by xn. Okay. Delta is equal to 1 divided by n into natural logarithmic of x naught divided by xn. There are three formulas. One is uh, delta is equal to ln of xn divided by xn plus 1. The second one, delta is equal to 2 pi zeta divided by root of 1 minus zeta square. Then third one, if we know the number of cycles executed by the vibrating body, the logarithmic decrement delta is given as delta is equal to 1 divided by n into ln of x naught divided by xn. So these are the formulas. Now, it's a one-page formulas. The one-page formulas here. These formulas more than sufficient to crack the problem with the longitudinal damped vibration as well as undamped longitudinal vibrations. So these are the formula. Coming into the first formula, omega n is equal to root of s divided by m. The second formula we know that natural frequency fn is equal to omega n divided by 2 pi, or fn is equal to 0.4985 divided by root of delta. Here fn is directly proportional to omega n, so here calling it as indirectly omega n is the natural frequency of the system, but the unit is radian per second. Coming into the frequency, it is hertz. Fourth one, critical damping coefficient Cc. Critical damping coefficient Cc, that is Cc is equal to 2m omega n. Critical damping coefficient Cc is equal to 2m omega n. Then next one, fifth one, damping ratio or damping factor. That is a ratio of damping coefficient to the actual damping coefficient to the critical damping coefficient Cc. So C divided by 2m into omega n. The logarithmic decrement, we know that these are the three formulas. Delta is equal to 2 pi zeta divided by root of 1 minus zeta square, or delta is equal to natural logarithmic of xn divided by xn plus 1. If number of cycles known, delta is equal to 1 divided by n into natural logarithmic of x naught divided by xn. That is seventh one, omega d is equal to root of 1 minus zeta square into omega n. 1 minus zeta square into omega n. So this is the equation. Now we are moving into the problems. The first problem regarding the damped longitudinal vibration. Now a vibrating system consists of mass 8 kg, spring stiffness 5.6 Newton per millimeter, and dashpot of damping coefficient of 40 Newton per meter per second. Then from this equation, the critical damping coefficient is First we need to write the given data in the problem. Now the mass m is equal to, here m is equal to 8 kg. 8 kg. Then stiffness K. The stiffness K is equal to, we can take it as K or S. Already we have discussed this formula itself S. I am keeping it as S. Yes. Here S is equal to 5.6 into Newton per millimeter. That is equal to 5.6 into 10 to the power 3. 5.6 into 10 to the power 3 Newton per meter. These two values are more than sufficient to identify the value of critical damping coefficient. To confuse the answer, here the damping coefficient was given in the problem. Now critical damping coefficient, coming to the formula, it's a critical damping coefficient formula. Cc is equal to 2m omega n is the critical damping coefficient formula. Use this formula. We are using this formula. What we are getting here is equal to critical damping coefficient. C suffix c is equal to 2m omega n. C suffix c is equal to 2m omega n. From this equation, Cc equation, now 2m omega n is equal to root of s divided by m. Root of s divided by m. Now substitute the value. 2 into 8 into root of s is equal to 55,600 divided by 8. The critical damping coefficient is given as, okay, use your calculator. I am using the virtual calculator here. 56 into 10 to the power 2 divided by 8 and into 8 into 2, that is equal to 423.32. The answer is here 423.32 Newton second per meter. Newton second per meter. Now from this equation, what we are getting here, the correct answer is option B is the correct answer for the given question. Option B is the correct answer for the given question. Next we are moving into the next question. The next question to you here, coming into this question, here the thing is mass is suspended from in this equation. A mass suspended from a helical spring vibrates in a viscous fluid medium whose resistance varies directly with speed. It is observed that frequency of damped vibration, 90 per minute. So here what we are writing here, the frequency of ft is equal to 90 per minute. 90 per minute. So it is equal to 90 divided by 60 seconds is equal to 1.5 Hz. 1.5 Hz. Okay. The amplitude decreases to 20% of the initial value at one complete revolution. So here what we are giving at complete end of the one complete revolution, that is x 1 is equal to x1 is equal to at the end of the one revolution, this reduces to 20%, that is equal to 0.2 into x0. The x0 divided by x1 is given it as 1 divided by 0.2, that is equal to 5. These are the given values here. Now we need to identify the frequency of undamped vibration. We need the value of omega n. Omega n we need to identify. Sorry, fn. We need the value of fn. Here, to identify the value of fn, we need the value of omega n. For that, first we require the value of zeta. For that, we are getting delta. So delta is equal to ln of x0 divided by x1. That is equal to ln of 5. So amplitude reduction factor is given as natural logarithmic of 5 is equal to 1.609. 1.609. We know that delta is equal to 2 pi zeta divided by root of 1 minus zeta square. From this equation, what we are getting here, so cross multiplying and total, what we are getting, cross multiplying and squaring 1.069 the square into 1 minus zeta square is equal to 4 pi square into zeta square. From this value zeta, here we need to identify the zeta value. Wait a minute, okay, I will multiply it and I will give the value here. It's a 2.59. So 2.59 into zeta square, we have to take into the right hand side. 4 into pi square, it is 42.06. 42.06. 2.59 so zeta square divided by 42.06. 42.06. So zeta is equal to 0.428. sorry 248, it's a zeta value. If you know the zeta value, then we know the relation in between the, again I am writing in the different equation here. Here from this equation omega d, from here omega d is equal to fd into fd into 2 pi. So fd into 2 pi is equal to omega d is equal to fd value, it is 1.5 into 2 pi equal to 9.42. Now we know the value omega d is equal to root of 1 minus zeta square into omega n. Now omega n is equal to, substitute that value, so 0.48, so 1 minus answer root of answer, we know that omega d 9.42 divided by answer is equal to 9.72. Omega n is equal to 9.72. Now we know the omega n value, from this value fn, so divided by 2 pi is equal to 1.55. so here the answer is 1.55. The answer for the given question is 1.55 Hz. The frequency of the undamped vibration is given as 1.55 Hz. Okay. Thank you so much for watching this video. If you are having any doubts, you can ask your doubts through the live chat also. I'm handling the special classes as well as regular plus class in the Unacademy platform also. Please stay in the Unacademy as well as YouTube live sessions. Okay, thank you. Thank you for watching.